Hi, this is Mrs. Gregerson. Since I can't be in school today, I've recorded myself going through the notes for you guys since we are starting out the next unit. So you will get your tests this week, probably on Tuesday, maybe Wednesday, depending on people who need to make up their tests. Just a reminder that your Quest homework is already posted and published. It's ready for you to start. After today's notes, you'll be able to do numbers 1 through 4, and the Quest homework will be due on December 4th by midnight. Your test for this unit is looking like it'll be on Monday, December 8th. So just kind of looking ahead to that. Be prepared. You can go ahead and get your notebooks ready to start out this unit. Make your title page for the unit. Make your Gems of Wisdom area ready to go. Even though we haven't been using that a whole lot, I have seen some people using it on their own, which is awesome, and we will be using it as we review for the semester final coming up in January. After your unit page, if you would like to make some pages reserved for your Quest homework, that seems to be working pretty well. And then if you want to get a page set up and ready to go for this section, you would be ready to go. So whoever is running the computer, if you want to pause for just a second right now while everyone gets their notebooks ready, that would be great. Thanks. Okay, as we go into this next unit, we are looking at work and energy for the whole unit. For the sections we're talking about today, sections 5.1 and 5.4, we're talking about work and power. So we've been doing forces, and we've been looking at forces at an angle and all kinds of vectors. We are going to take into account those forces now and stuff at angles with components and apply that now to work. So here we go. I have a couple different scenarios for you here. If you would take a few seconds and talk with a neighbor for each one, and you are deciding, is work being done? So first scenario, Mrs. Gregerson pushes on a goalpost for an hour. So turn to someone next to you, decide yes or no, is work being done? Jot down your answers for these somewhere in your notebook, and you can compare to the answers that we'll go through in a little bit. Number 2, Mrs. Gregerson carries a football down the field for a touchdown. Yes or no? Oops, my phone started ringing after that last one. Alright, the next one. Mrs. Gregerson fumbles the football. Yes or no, is work being done? Jot down your answers, remember. Number 4, Mrs. Gregerson recovers the football. Or fumble, excuse me. Number 5, Mrs. Gregerson throws the football for a touchdown. This is all in my dreams of being an awesome football player. And number 6, Mrs. Gregerson mows the football field with a push mower. So yes or no for these, is work being done? Here we go. Number 1, no, work would not actually be done if you push on a goalpost for an hour. You might be tired, but in physics world, work would not be done. You'll find out why later. Number 2, if you carry a football down the field for a touchdown, work is not actually done in physics world. And again, you'll find out in a little bit why. Number 3, Mrs. Gregerson fumbles the football. Yes, work would actually be done in physics world. Number 4, recovers the fumble. Yes, work would be done. And number 5, throwing the football for a touchdown. Yes, work would be done. And number 6, if you mow the football field with a push mower, yes, work would be done. And you would likely be very tired as well. So here's my next question to pose to you. What is required to do physics work? Talk with a neighbor next to you. You might want to pause the video for a second. I want you to come up with an answer and jot that down in your notebook as well. Okay, now that you have an answer to the question, what is required to do physics work, I'm going to tell you 2 things. In physics, in order for work to be done, there must be a force and a displacement. And that force must cause the displacement to happen. Okay? So number 2 is probably the one that seems to be most confusing, to me anyways. If you carry a football down the field, yes, the football is moving, but carrying it just holding it is not causing the football to move. So the force of holding it is not causing the displacement. So in physics, you have to have a force and a displacement, and that force must cause the displacement to happen. So first, work. To put it simply as an equation, work is going to equal force times distance. Pretty simple. We've talked about forces with newtons, and now the distance, how far you move something, will be incorporated into the work. The units for work, well, if you take newtons times meters, you get a joule. So joules is going to be the units we talk about. Force and distance have to be in the same plane, so we're talking vertically, horizontally, or at angles. The force and the displacement have to be in the same direction. So if you're pushing something forward, both of those forces might be horizontal. If you're pulling something up, the force and the displacement would both be vertical. So in those cases, work would be done. Or at an angle, same thing. Force and distance have to be in those equal planes. Work can be positive or negative because it is going to be a vector with direction. If it's positive, force is going to be in the same direction as the object is moving. If it's negative, force will be in the opposite direction the object is moving. So that would be if the force is opposing the motion, you would say, then that work would be negative. We'll pause the video here for just a second, finish these notes. If a force is at an angle, so here's going to be our components again. If the force is at an angle with the ground and the object is moving along the ground, think here you pulling your little brother on a sled and the force going through the rope would be at an angle. You're going to have to find the component of the force that is in the same plane of motion as the object. So most of the time for the problems you'll be doing, you're going to have to find the horizontal component. So that same equation that we talked about before, with the x component of the force being the force times cosine theta, that's going to show up again. If you find that component in the same direction as the motion, then you can use that to determine the work. So again, think of pulling your little brother on a sled. Alright, here's a clicker question, but I'm not going to hand out clickers because we don't want the sub to have to deal with those. So we'll go over these questions, pause at the end of each question, talk about it with a neighbor, decide which one you think is going to be the right answer, and then I'll reveal the answer for you. So this first one, using a constant force of 40 newtons, you push a box which weighs 65 newtons, a distance of 2 meters up a ramp, your force being parallel to the ramp. How much work do you do? So talk with a neighbor, and then we'll come back. Okay, now that you've talked with a neighbor, hopefully you realize that your motion and the force are in the same direction, so you can just take your force times your distance. 40 times 2 would give you 80 joules. And that force is in the same direction as the motion, so it would be positive. Next one. While you push the box a distance of 2 meters up the ramp, the frictional force on the box is 45 newtons. How much work does friction do? So again, talk with your neighbor, pause the video, and then start it again when you're ready. Hopefully you notice that if the force is in the same direction as that movement again, you can just take your force times your distance, which would give you 90, but you have to decide is it positive or negative. Well, in this case, the force is going to be opposing the motion, because friction is trying to make it go the opposite direction, so it would be negative 90 joules as your answer. Next one. While you push a box of 2 meters up the ramp, the gravitational force, here's your gravity, is 65 newtons. How much work does the gravitational force do? This one's a little more tricky. Think about which direction the part of the weight will be acting on the box in this plane. Talk with your neighbor, we'll come back. Hopefully you notice that you would mainly be talking about the parallel weight component because that's going to be the one that's acting in this plane of motion, but it's going to be opposing the motion. So I'm not expecting you to figure it out because I'm not giving you an angle, but if you figured out that parallel weight and use the angle, you would find that it's somewhere between 0 joules and negative 130 joules. And my box is a little off here, I realize. Okay, last force we need to talk about is the normal force. While you push the box a distance of 2 meters up the ramp, the normal force on the box is 60 newtons. How much work does the normal force do? Talk with a neighbor, pause the video, and come back. This question is testing whether you know the direction of your forces and whether you know that they have to be going in the same direction as the motion in order to count for work. In this case, the normal force is perpendicular to the direction of motion, not in the same direction, so it's not going to count as part of work. That normal force is doing 0 joules worth of work. Okay, there's a couple examples here. You will have a video at the end of the notes to take you through working through the examples. You will be able to copy them down and do the work then. So I'm just going to skip through these and then talk about power. In physics, power is the measure of how fast you do the work. So we've gotten your work all figured out, force times distance. Now we're going to do power, take into account time. The equation for power is going to be the work, which we just learned how to calculate, divided by time. That's going to help us figure out how fast you're doing the work. Time is going to be in seconds. The label for work is joules again. And the units for power, if you take joules divided by seconds, you get a watt. And we'll just use W for that. Sometimes we talk about like kilowatts, even megawatts, going up bigger than that. 1,000 watts would be 1 kilowatt, similar to how 1,000 meters is 1 kilometer. You can pause here if you're still taking notes. All right, here's another clicker question without clickers. Which requires more work? Walking up 2 flights of stairs or running up the same 2 flights? So pause the video, talk with a neighbor. Okay, in the equation for work, hopefully you realize that time is not a factor when you're just taking force times distance. So you would be doing the same work whether you walk or run up the stairs in physics world. Now, which requires more power? Walking up 2 flights of stairs or running up the same 2 flights? You can pause the video, talk to a neighbor. Hopefully you realized that when you're talking about power, time does count. So running would give you a greater amount of power required to go up those 2 flights of stairs. Okay. Again, there are 2 examples here that the next video are going to take you through, so don't feel like you have to copy them down right now. They will show up again. Hopefully you got all these notes down today. If you didn't, they are posted on the Google site. And if you have any questions, we'll be able to go over any tomorrow. Hopefully I'm back tomorrow. All right, guys. There's also a vocab assignment that your sub will be telling you about. It's written down in the sub plans. You'll do that in your notebook, and it'll be due on Wednesday. All right. Have a great day.